Hello. So, welcome to week 5, midterm project week. Very exciting. I am going to cover the midterm project instructions, and I'm also going to walk through an example. So, let's get started. So you will want to make sure that you check back and look for anything that is up here in the instructions and examples. That's where you would find this link. So you probably started here. I also have a short video on the formula sheet that is here in PDF format with an explanation of the formulas on that page. But we're going to dive into the sections down here for the midterm document and instructions. So the first page here is just a simple rundown of instructions for the midterm. So let's go there first for just a moment. So it says to download and review all the documents, which I'm going to walk through. The packet of documents includes formulas for 2D and 3D objects. That's the formula sheet. That also has, again, a short video that explains the formula sheet. Then you're going to need the instructions for the midterm project. I have them loaded in both PDF formats and MS Word formats. The reason is you have a choice. You can either use the PDF, print it out, handwrite your answers, scan it, and submit it. Or you could start with the Microsoft Word document if you prefer to type into the document directly. Then you're going to want to save it and save it as a PDF document because you can only submit PDF documents. So just to recap, you have the choice of picking the PDF or the Microsoft Word document to start with. I'll show you that in a moment. And then you also want to get the document that is the assigned part for the midterm. I'm also going to talk about that part. I'm going to first talk about an example part, which you may not use for the midterm. And then I'm going to talk about the part that's assigned for the midterm. So I'll try to be clear on that because sometimes that adds a bit of confusion. So you may not use the sample example part that I'm going to walk through for the midterm. You have to use the assigned part. Okay, so once you complete it, you will submit it to the midterm document assignment found in the module for week 5. We have some assumptions. So let's just walk through those real quick, and then I'll revisit these as I'm walking through the assignment. So you'll ignore any radius, corners, or bend allowances or anything like that in the part, anything that is a rounded corner, that sort of thing. You're going to always use 3.1416 to estimate pi. That will help us just be consistent where everybody's using the same number. The instructions specify to calculate the heaviest part allowable. So I'll talk about that as well. And then you're going to round any and all of your final answers to the nearest thousandth decimal point. So thousandths, how many thousandths? How many decimals are there for a thousandth? That's right, that's 3. So we need 3 decimal places. And then there's just a little hint here that you may have information that's given that you might not use for anything. You might not use all given information. Okay, so that's the midterm project instructions. Let's go back to the modules here and check out what else we have in here. Wait for it to finish loading. Okay. So we see down here in midterm documents and instructions, I have the midterm project instruction we just went through, and right underneath that is the midterm project in a .doc. That's a Microsoft Word document, or the same exact document. There's no difference between these two other than the fact that this is a .pdf. .pdfs can be opened on more devices. So that one is there for you if you don't want the Microsoft Word version. There is no difference in those two documents. If you want to be able to type into it and create an electronic file from the Word doc, I would use this one. If you don't care and you just want the document, I would say grab the PDF. All right, so that's there. And then you'll see underneath that then is the part that's assigned to you for the midterm. This is the part that you will use, you're expected to use. And I will walk through an example, and I'll also then at the end of this video pull up this aluminum spacer that you're going to use. Then you see the formula sheet repeated. This is the same sheet as up above. And then you see the midterm project assignment submission. That's the assignment that you will assign your final version to. So you'll submit it there. And that is, that will only accept a PDF version of this document. So a lot of students use a scanner for their phone to scan their final handwritten document. So the one I use on my phone is called Cam Scanner. I have an Android phone. I know some students have used Turbo Scan. If they have an iPhone, it's up to you what you want to use, but somehow you need to have technology so that you can get it into a PDF format to be able to submit it to this midterm project. Okay, so let's take a look at the project and take a walk through it. Okay, so back here in our module, I'm going to go ahead and look at the Word document version because it's easy for me to draw and kind of write in that one. And I'm going to walk through it using a sample example part. This is not the part that you're assigned. This is just a part that I'm going to use to kind of help us so that you can maybe understand this more fully. Okay, so it will help. Okay, so I grabbed the midterm document. You see it says midterm project, measurement area volume and unit conversion. This midterm is worth 50 points. You want to make sure your name is in here and your information. You want to read all the instructions before you start doing anything, right? We always start with what we know. So we're going to download all our technical information on the part. Take a few minutes to look through that technical information. Then you want to make sure that you're scrolling through documents all the way because I've left some space for you to do work, so you don't want to miss anything. Okay, so you're going to complete the project details. The first thing that you're going to complete is after you review all of the information, locate the information you need and list what you know. What is it that you know about the part that you are assigned? Then you're going to look at, review all the information and tell me, what are you trying to find? What is it that you're trying to find? And then part C here is what formulas do you need? So this last part, the part C, you might go back and forth to part C and go, oh, I need another formula. I need to add that to my formula toolbox at the top. You're going to include a technical sketch and a written description of your part. So I'll show you what I expect for that. And I have a note here for the rest of it, 4, 5, 6, and 7, emphasizing 4 and 5. For purposes of this project, we will calculate the heaviest allowable part, i.e. the heaviest part allowed by the tolerances given. For example, a dimension of 1.25 inches plus or minus 0.03 inches would have the heaviest size of 1.25 inches plus the 0.03 tolerance, which would mean the largest or heaviest size would be 1.28, as long as the feature is not a hole, right? If the feature that's dimensioned is a hole, then the heaviest size would be the smallest hole, right? Because a smaller hole in a part would mean that there was more material. So if we were talking about a hole, the heaviest size would be 1.25 minus the 0.03, or a whole size of 1.22 inches. That'll make more sense when I go through the example. All right, number 4, then we're going to calculate total surface area of your part. Make sure that you include all your formulas in the formula section, and make sure that you have formulas and calculations clearly written so that I can follow it. I do award partial credit for the midterm, but only if I can read it. If I can't read it, I can't grade it, and I can't give you any partial credit. And if you don't show your work, you don't get credit for anything. So make sure you show your work and make sure I can follow it and understand it. Number 5, you're going to calculate the volume. So we're going to calculate surface area for number 4, volume of the part for number 5, mass for number 6. So 4, 5, and 6 are calculations. And then number 7 is an evaluation and analysis of your results. Okay, so let's walk through an example. First thing says to download your technical information. So again, this is an example part, not your part, okay? My example part is a washer. So I have a 3/16 stainless steel washer here. So that is my part right there in what's called a 3D or isometric drawing. This is a screenshot from McMaster Carr. So you see that I have some technical information here. I know what material is, I know what screw size this washer is intended to mate with, and then I have an ID and an OD. ID and OD is telling me, get my stuff moved around here so I can draw on it. ID and OD is inside diameter. This is my inside. And this is my outside. Okay, so that's my ID and my OD. So my inside diameter is 1.625, my outside diameter is 3. Okay, so we can kind of start to envision this here is 3 inches, right? And then my OD goes across the inside here. That is 1.625. So you can see I can start to envision or visualize what's going on here. All right, and then I have a thickness. So thickness would be this, right? I have a thickness, and notice that my thickness is a range. It's a range of possible choices. So I have a thickness that could be 0.153 all the way, so there's a dash there. So the smallest thickness that is allowed is 0.153. The largest thickness is 0.213. So remember that for our project in the instructions, it said we are measuring for the heaviest part. So I would want the largest part possible. That means I want the thickest washer possible. So I'm going to use the 2.213 inches here. All right. So that's the thickness of my washer. It's a flat washer. My system of measurement is inches. I don't have a hardness rating. It does have a standard that it meets, and then it has an ID and OD tolerance of plus or minus 0.010. Now, again, we're going to evaluate the part at its largest or heaviest size. So what does that mean for my ID and my OD? Well, since ID is listed here first, let's look at the ID. For my ID on this part, or my inside diameter, what would make a bigger, heavier part? A smaller ID or a bigger ID? Well, that's a smaller hole or a bigger hole question because the ID is referring to the hole diameter. And for the part to be heavier, a smaller hole would mean a heavier part. Aha. So what that means is my 1.625, which is called the nominal or the base dimension, I'm going to subtract my tolerance, because I want to make the hole smaller. The smallest possible hole would be minus 0.10. Whoops. That's why we made erasers. 0.10. Right? That would be the smallest hole. Okay, so I'd have 1.615. That's what I would use. Now my OD, which is not a hole, outside diameter would be my 3 inches here. My OD, what do we want here? Do we want to make it bigger for a heavier part or smaller for a heavier part like we did with the ID? That's right. We want to make it bigger because it's not a hole. This is now the outside dimension of that washer. So to get the largest part possible, I'm going to take my 3 inches and add my tolerance down here of 0.010. I'm going to add that to that dimension, and that's going to give me 3.010. I should have put my zeros on here. There we go. Get all those zeros in there. So we're at 3.010 for my maximum outside diameter. All right, so this is going to give me heaviest part. Right, I've got my thickness at 0.213, that's maxed out. I've got my smallest ID or my smallest hole, and I've got my largest OD or my largest outside diameter of the part. Okay, so now let's take a look at what we're supposed to do with all this information. Okay, so the first section says, what do I know? Well, what I know is, I know my maximum OD is equal to 3.010 inches. My minimum ID is equal to, and you could call that whatever you wanted, but minimum hole, maybe I'll even put the word hole in here so we can keep remembering why we need the smaller number there. My minimum hole ID is 1.615 inches. And I know that my thickness is equal to 0.213. And that's actually my maximum thickness that's allowed for this part. All right, so that's what I know so far. I also know that my part is a cylinder. I know it's a cylinder, and it's really a flat washer. That's what it is, but it's in the shape of a cylinder. Okay, what are we trying to find? Well, I want to find, I will calculate the volume, the total surface area and volume and mass of the part. And I will analyze my results. And then formulas. Well, I'm not quite sure what formulas I need yet, but I'll come back to here once I kind of figure it out so I can go back and forth. And now if you handwrite this, it's totally fine. I'm only typing in here. You're going to see me drawing too, so that you can read it clearly and I can do it on the screen. But you could print this and you could handwrite on there. Just make sure you know that you have to scan it and then you have to submit it as a PDF. So we'll come back to the formulas here in a second. Okay, so 1.02, the second part here, is a technical sketch. So we need a written word, like sentence description of the part, and we also need a technical sketch or graphic. So here is my written description. I have the part is a 316 stainless steel flat washer. For 1.5 inch screw with a base ID of 1.625 inches and a base OD of 3.000 inches. My sketch includes the dimensions needed for the heaviest possible part. All right, my sketch is going to look something like this because I have a flat washer. Now again, and you're going to have something similar to this, I have a three-dimensional, but a sketch, a technical sketch, what I really want is a view where I can really dimension that drawing, and I want to do it in two-dimensional if at all possible. So do your best. It's a sketch. It does not have to be to scale. It does not have to be perfect. I'm just looking for a sketch of what your part actually looks like. So mine would be something like this. I have a circle. I have an OD on that circle. Actually, I'm going to make my OD a little bigger because it is, in fact, a little bigger than that in relationship. So I'm going to make it kind of somewhat reasonable. Ooh, see, sketch. All right. And then I would have a side view. This would be my front view. And I would have a side view that would, you don't have to draw these in, but it's going to be the same height in the side view for a part like this. Even though it's a round part, the side view looks like a rectangle. And the side view is where we're going to get our thickness. Okay, then I can erase my projection lines here. Okay, so that would be my side view. Front and side. And then I'm going to put in my dimensions for the part. So I'm just making them different colors so they kind of stand out, hopefully. So I would have my maximum OD over here of 3.010. That's my max. And I would have my ID. I could put it in here because I have room. Or I could have put it a leadered line, if you know what that is, and I could put it out here what the diameter is, but I'm going to put it right in here. Again, I'm not looking for like if your drawing is perfect or anything like that. It's just if you get the idea. So this is 615. That's my minimum hole, my smallest hole. And then my thickness I'm going to show over here. And because it's so small, I'm going to put it on the outside over here. And my maximum thickness was 0.213. So there's my drawing. There's my technical sketch, right? And here you go. Not to scale. If I can get my mouse to work. There we go. Not to scale. So sorry, it's a little messy. If you hand draw it, you can probably do a little nicer job than I can do with my drawing on my screen. But hopefully you get the idea of what we're going for here. Written description, and also then a part drawing, and put your dimensions on the drawing, because then you'll be able to use this going back and forth and it will help you. All right. So the next piece is calculate the surface area. So we want to calculate total surface area of our part. And remember that this is basically, if you were going to paint it, how much paint would you need? So if I come back here to my drawing of my part, right, of my ISO, it would be what's dark gray, right? It's what's charcoal. So if I look at this and I think about it, I could label some surfaces, right? I've got an edge surface here. That's number 1. I've got a face, number 2, and I have an internal edge here, 3. And then on the underside there, I have another 2, right? So 2 is repeated front and back. Top and, let's call it top and bottom. Top and bottom, right? Because this number 2 surface looks the same on the bottom as it does on the top. But surface 1, which is the lateral area here, and surface 3 are different. Okay, so what are we going to have to do to figure that out? Well, we're going to make a little roadmap before we start doing anything. So we've already walked through what we know. Let's write down what we would have to figure out. So for total surface area, I would need lateral side number 1 that I labeled on that drawing. I need lateral surface number 3. And I also need the face, which we labeled number 2, times 2. Or add it twice, but I need 2 of those. These surfaces, let's go back to here. Let's label them that way. These surfaces, this would be L1 because it's lateral area. And I had L3. And I have, for face, I have face 2. And I'm going to have that twice because of the top and the bottom. Okay. So how do I calculate lateral area of a cylinder, right? Because that's what we're dealing with is a cylinder. So I'm going to go to my formula page. We're going to look at our cylinder formula. Well, surface area of a cylinder right here is S is equal to 2 pi RH. That's the lateral surface area, plus 2 pi r squared. 2 pi r squared is the top and the bottom. I don't really want that. I want to just deal with the 2 pi RH first. So we're going to write that down. Let's see. Lateral surface area that means around the outside, is equal to 2 times pi times r. Let's do this so it makes it more clear. times pi times r times h, right? Or you could handwrite that out, or I could draw it in there, right? 2 pi rh. Then I have a couple choices. My lateral surface area of, I should put the word cylinder in here. I'm gonna put cylinder. That actually will work for L1 and L3. Then I have a choice. I can calculate the face of this thing using the area of one circle minus the area of another circle. So I could take the area of the circle like the hole isn't there, and then calculate the area of the circle, the hole, and subtract. Or I could choose to be a little fancier, and we could look at the surface area of an annulus. So an annulus is basically what this thing looks like, right? Annulus is a ring. Look at that. So is this. So we could just go ahead and take that formula, and maybe that would be a little faster. Now, it wouldn't matter. You could do either one, but I'm going to try this one because it looks pretty cool. So that is, make sure I get this one on there, right? So that is the area of an annulus. I'm going to put ring so you remember what that is, or so I remember what that is. That's equal to pi times capital R squared minus little r squared. All right. So that would take care of one face of my washer, because this thing looks remarkably like a washer, right? If we look at that. So we're calculating the area of this face using big R, which is the bigger radius, and small r, which is the smaller radius. All right, so let's try this and see where we get. So if I go back and look at my sketch, I also can pick some things off here of my sketch so I can kind of use this to figure out what I need. All right, so the first formula for the lateral surface area of a cylinder, I need radius and I need height. So let's look at radius first. If we go back up to here, we have two diameters given, right? An OD and an ID. Those are diameters, inside diameter and outside diameter. I need radius. So I'm going to just go ahead and calculate the radius 1 and 2. I'm going to call them radius 1 and radius 3 since that's how I chose to label these. You can pick whatever labels and letters make sense to you. That's just what I kind of went with. All right, so my radius for my outside is equal to my 3.010. That's my diameter divided by 2. My radius is going to go with my lateral area on the inside. I'm going to call that R3. Is going to be my 1.615 divided by 2. So we need those to be able to get started with this thing. Okay, so get out our trusty calculator so we don't make any mistakes. at least hopefully. So here we have 1.505 inches. And here we have 0.8075. Now you might think at this point, I could go ahead and round that because my answer is going to have 3 decimals. No, do not do it. Don't stop yourself. Nope. Leave it alone. Carry the 4th decimal place until the end of the problem so you can minimize rounding errors. You're still going to have some rounding errors because of pi and that sort of thing, but just trying to minimize them as much as possible so that you don't get into trouble. Okay, so there is my radii for my circles, right? So it would be as if, let me get my handy dandy here thing. So if I drew this in here, whoops. So now we have from the middle of this circle to the outside, that's R3, right? And from the middle to the way outside, that's R1. That's R1. This is R3. And I just did 1 and 3 because that's when we started labeling the faces. Well, you can see that. Okay, so that's my radii. So lateral surface area 1. L1 is equal to, I gotta make that look bigger or better. L1 is equal to 2, it's this right here, 2 times pi, we're going to use 3.1416 times my R1, which is 1.505 inches, times my height. Well, we don't know what the height is. Let's go find the height. Let's go back up here. Well, height, you might think height is this. You might think it's this right here. But that's actually a diameter, not height. Height for a cylinder, let me bring this picture back over here. Height is this, right? Height is the thickness. So my 0.213 is actually my height. So I will write that down here. So my height is equal to my maximum thickness, or 0.213 inches. All right, so that goes in here, 0.213 inches. All right, so that's my lateral surface area of the outside rim, outside edge of the washer. So L2, or I'm sorry, L3, which is the inside edge, is the same thing, only with the other radius. So it's 2 times pi times the smaller radius, 0.8075 inches, times the height, which is still the same thickness because the flat washer is the same thickness all the way through the part, right? So it doesn't matter if it's the inside hole or the outside hole, the edge of the hole. Okay, so we've got both of these worked out, and then I can just crunch the numbers in and I will get values for surface area. Now note that 2 doesn't have any units, 3.1416 or pi has no units. But the next two things, the radius and the height or the thickness, both have inches. So we're going to take inches times inches. If we do that, what do we get for a unit? I'll let you think about that for a second. What do you think? What's the unit that we're going to get here? That's right, it's square inches. All right, so here I get I get a bunch of decimals. I'm going to carry 5 of them for now. So I, again, minimize my rounding errors. So I have 0.1417. And that is square inches. And then I'm going to do the second one here. 2 times 3.1416 times 0.8075 times 0.213. And I'm going to get another 5 decimals. There's more than that. I'm actually rounding at 5, but 1.08069. I'm going to keep both of those. And that's square inches. Okay. So that's, now what do we have? What we have, I'm going to erase some stuff off of here so we can see what we are calculating. Now we have this edge, just the edge, and we have this inside edge, just the edge. Just the edge, like if we painted the inside edge. What we need now is the face 2 top and bottom. All right. So how are we going to do that? Well, that is my ring. That's my annulus. So my F2 my face 2, one of them, is going to be pi times, so I have 3.1416 times quantity, so that parentheses is important because we have to do the parentheses first. My big R, that's my bigger radius, so that's 1.505. 1.505. And this is going to be squared minus the little r, the smaller r, which is 0.8075. 8075 squared, like that. Now we're going to remember that this is inches and it's getting squared, and it's inches and it's getting squared. So we're going to have the same unit, and we have to have the same unit on this as we had in the first 2 answers. We're going to end up with square inches because of these squares. So we do the squaring first. So we take the 1.505 times itself, or you could use a square button on your calculator. Either way. And you get here, I'm going to get 2.265025. And now this is inches squared because I squared it, minus 0.8075 times 0.8075, which is 0.65205625. I know it's a long decimal. Inches squared. Now, as much as you can keep decimals until you get to the n and then round to the 5, you're going to be better off. So that's why I kept everything that I had. All right, so those are now square inches because I squared the numbers, but I have to remember that I now have to subtract and multiply times pi up here. All right, so I'm going to subtract these 2 things from each other. And I get, still I have my pi. Now, if you could do this in one big shot, you don't have to write this many steps down. I'm just doing it so that I hopefully keep everybody with me. What I get was 2, 9, 6, 8, 7, 5. And that's inches squared. Now all I have to do is multiply by pi, 3.1416. And now here at the end, I'm going to just round it to the nearest 5 decimal places. So 5.06730. That's square inches. Now, careful to remember, this was the face. This is the face of the washer, right? This is this right here. You can't really see that, but that's the silver face. How many of those do we have? That's right. We have 2. So this has to get multiplied by 2. All right. So I'm going to take that times 2. That gives me 10.13461. I rounded a little bit there. That's square inches. Now remember what we were trying to calculate. We're trying to calculate total surface area. So now I have my lateral outside, my lateral inside. That's this side of the edge of the ring on the inside and the outside, the hole. And then I also have the faces. So what am I going to do? I'm going to add these all together. I'm going to add the 2.01417 plus the 1.08069 plus the 10.13461. That's going to give me total surface area. Okay, let's do it. If you have history on your calculator, it can be super helpful with this. Are you doing it with me? I hope you're doing it with me. Okay, so for my grand total, I get 13.2294 square inches. Now, instructions for the project say to round to the nearest thousandth. That's 3 decimals. So that means I want to round to this decimal here. So I look to see what's behind it. Well, behind the 9 is a 4. So that means I don't round up. So I just have 13.229. So my answer up here is 13.229. And don't forget your unit labels. You will lose points. This is square inches. All right. So that's total surface area. Cool. All right, let's check out volume. So the next thing is volume. I'm going to calculate the total volume of the part, and believe it or not, volume is a little bit simpler than the area. So usually students are happy when they get the area completed because that's actually the more challenging part. All right, so we got to think about what is it that we're calculating here for this part. Well, we have 2 rings really, right? Well, we've got a cylinder in another cylinder. So there's a couple ways we could approach this. We could take the volume of a cylinder and calculate it for the outside like it was a solid part with no hole. And then we could calculate the cylinder on the inside and we could subtract it. So the cylinder would, the hole itself is a cylinder of air, right? It's a cylinder of space. So we could take bigger cylinder minus the smaller cylinder and have the total volume. That's one way you could do it. Another way you could do it is you could take, and this would work for any part that has a behavior where the top face and the bottom face are parallel. So to do that, we could take the face. I'm going to erase some stuff here so we can kind of see what I'm talking about and what I mean by face. So another way we could do it, so we could take one big cylinder minus another cylinder. That's one way to do it. Or we could take the area of the face of the part, which is the ring that we calculated. One face, that was our F2, right? So this area here, which we calculated as an annulus, and we could multiply any area where one face is parallel to the other face, is just the volume then is equal to the area of the face times the height. So this works for all sorts of things, and it's actually really cool. If we think about it, the reason this works is think about our box that we've used over and over and over again. The only difference between volume and area of a box, area is length times width. That's what we usually say. So let's say this is length and this is width. Actually, let's say it's this. The area of this face over here is length times width. Well, the volume just adds one more dimension. Volume is length times width times height. So if we know area, all we're missing is the H, right? Because these are already included in the area. So we're going to do it that way. It's a little faster. It's a little more complex. But you could also, if that confuses you, you could use the cylinder method as well. Okay, well, let's go back to here. So what this means is we're going to go back here and we're going to use this number right here. One face, because we took it times 2, one face is my 5.06730. Okay, so I'm going to say the area of the face which looks like this, is equal to 5.06730. 5.06730, and that is in square inches. Okay, got it? Cool. All right. My volume is equal to the area of my face times the height. Well, that is going to be equal to 5.06730 square inches times height. Remember, height for us up here is the thickness. Height is thickness. So height is equal to 0.213 inches. I'm going to write it like this. So now I'm going to have inches times inches squared times inches. What are we going to get for our unit there? What do you think? What do you think? That's right. We're going to get cubic inches, right? Because we have square inches here times inches again is going to get me cubic inches. So I'm going to go ahead and do the number crunching part of it. So my 5.06730 times my 0.213, which was my maximum thickness, maximum allowable thickness, And that gives me 1.079334 cubic inches. And again, I'm going to round to the nearest 3 decimals. So I'm going to have 1.079 because the 3 behind the 9 means that I don't round up. And that's cubic inches. All right, that's my volume. Piece of cake. Now again, you could have used a cylinder minus the hole, which is also a cylinder. Totally would work. You should get the same thing. All right, let's look at the next part. The next part is mass. Now what we're going to do is calculate the part's mass based on density. This is a unit conversion problem, right? So we're going to assume your part is made from aluminum. Use the density below, calculate the mass of your object in grams. And hint, remember density is a ratio of mass to volume, and you're going to show all your calculations and enter your final answer in the space provided. Okay, so what do we know? We know that density in this part is 2.7 grams per cubic centimeter. We know that density is a ratio of mass to volume. I'm trying to find mass. So density is a ratio of mass to volume. Well, I know what the volume is of my part because I just calculated it. My volume of my part is 1.07934 or 1.079. 1.079 cubic inches. Well, what I have for density, my density is 2.7 grams per cubic inch. I want to find mass. Well, one way to tackle this thing would be to solve this equation for mass. That would help us. Or we can approach this as a unit conversion problem with what I lovingly call brackety in former videos. So let's talk about it both ways. So if we imagine, I'm actually going to change one thing so this doesn't get confusing. We're going to use a capital D for density and little d will be diameter from before. So if density equals mass over volume, and I want mass, I need to move my volume to the other side. Well, I can do that by multiplying both sides by volume, right? Oops, that happened there. Okay, so I can move the volume over by multiplying both sides by volume, or I can swing the V over, right? And what we end up with is volume times density equals mass. Okay, so we could calculate mass knowing that, but our problem is I'm in grams per cubic centimeter. I want my answer in grams, but my number right now is in cubic inches. This is where brackety comes in. So let's just tackle it this way as well. I know that I have 1.079 cubic inches. I need something to help me convert cubic inches to cubic centimeters. Well, in earlier videos, or you could look this up, we know that 2.54 centimeters equals 1 inch. But we want cubic inches. That means we have to cube my 1 inch. If we cube my 1 inch, that means we also cube my 2.54 centimeters to get cubic centimeters. Okay, if we do that, the 1 times 1 times 1 is just 1, right? But my 2.54, I have to cube or take 2.54 times 2.54 times 2.54, and I will get 16.38706 cubic centimeters is equal to 1 cubic inch. Okay, that's our conversion factor, one of them anyway. I'm actually going to erase this and move it down a little bit. Other thing that we could put into brackety if we didn't want to use this equation down here is if I know density is a ratio, that means that my 2.7 grams is equal to, if I have 2.7 grams per cubic centimeter, 2.7 grams is equal to 1 cubic centimeter, right? This is a rate, all right? So we could do this all in one big shot. We'll take our original number, 1.079 cubic inches. And now with brackety, or I'll write it the more classic way down here on the bottom. Actually, you don't need it. It's more clear if I do it this way. With brackety, to revisit from my video from the measurement from week 3, we know what to put on the bottom because it cancels out. So we need cubic inches to go on the bottom. Well, over here in my conversion factors, I have my 16.387064 cubic centimeters is equal to 1 inch cubed. That means my 1 inch cubed has to go on the bottom because I want it to cancel. The thing that goes with it, the equivalent thing to that, is my 16.387064 cubic centimeters. All right. So what happens is cubic inches cancel out because they're diagonal. Anything diagonal, or top and bottom, I should say, anything top and bottom will cancel out. Now I have cubic centimeters. Well, my other conversion factor, if I can think of a rate as a conversion factor, because it is 2.7 grams equals 1 cubic centimeter. That's my density. What this means is for every cubic centimeter of volume, I have a weight of 2.7 grams. So I could go ahead and plug this in. 1 cubic centimeter, let me change my color. 1 cubic centimeter, because that has to go on the bottom to cancel out, is equal to 2.7 grams of weight. Now my cubic centimeters cancel out and I have grams on the top. Grams is what's left over. It does not cancel. That's good because that's what I want. Now I can simply multiply across the top here. This is multiplication. This is multiplication. I divide by what's on the bottom, but everything down here is 1, so it's not going to matter anyway, but that's what happens with these. So I'm going to take 1.079 times the 16.387 number times the 2.7. All my units cancel except for grams, so I know I'm in grams. All right, let's do it. 1.079 times 16.38764 times 2.7 is, voila, 47.740 grams. So then you ask yourself, does that make any sense? Well, a number 2 pencil, unsharpened, weighs anywhere between 2 and 4 grams. Really light, right? This is a 3-inch washer. So that's a pretty big washer. 3 inches. That's my estimate of 3 inches. It is fairly large, so it actually makes perfect sense that it can be around 47 grams if I can kind of imagine how much a gram is from a number 2 pencil, which is really quite light. Okay, so that makes some sense. Seems reasonable that we could get to there. That's how we get mass. So then I would put that answer for mass up here in my box, 47.740 grams. All right. So the last piece of the project then is the error analysis. So this is, if you're imagining that you had these parts, you knew what they were supposed to weigh, you calculated how much it was supposed to weigh in volume, and then you actually physically weighed the part, and you were writing an analysis of why they were different. Why would your calculated volume, which you convert to mass, so we calculated it from measurements on a drawing, it's supposed to weigh 47.740 grams, according to our calculation. But the actual thing, when I weigh it, does not weigh that. It weighs some other number when I physically put one on the scale. This last piece, which I'm not going to do, I'm just going to talk about it, is why would the two be different? Why would the scale weight ever be different than the weight that we calculated on paper? You have to have at least 3 reasons, right? So at least 3 reasons, at least 3 reasons. And you cannot use, I made a calculation error as a reason. That's not a reason. I mean a real reason. Like, what's a real reason why a real part versus a part that's in a CAD drawing, why would they ever be different? So at least 3 reasons. And they should be explained completely. So complete sentences. And so I should truly understand how you have come to the conclusion that that would cause an error. Okay, so that's the last piece. All right, thanks for joining me. It's been a pleasure. Have fun. If you run into trouble, as always, you know what to do. Please contact me, message me. I will have office hours that you can pop into if you have questions. If those don't work for you, please reach out and I could set up a special time or answer questions via email. All right, have a great week. Good luck. We're more than halfway done. Hooray.